Hello everyone, welcome to 321 Gang's webinar, Simplifying AutoSAR Advances in Modeling and Generation of Classic and Adaptive Applications. My name is Kara Rawlings. I'd like to tell you a little bit about 321 Gang before we dig in. So 321 Gang are a platinum IBM business partner and a scaled agile training partner. The Gang are the continuous engineering experts and an industry leader in scaling lean and agile practices. We offer our clients expert IBM and SAFe consulting services, training, and software tooling solutions to accelerate and drive results in the most complex, highly regulated systems and software engineering environments. 321 Gang's engineering expertise can help. Whether you're facing regulatory, economic, or technological challenges, 321 Gang offers industry-focused training and consulting. Talk to us today and learn how we can help deliver your solutions. Please take note of the question box in your control panel. We'll be accepting questions throughout the presentation and we'll be addressing them at the end. Today we have two presenters, IBM's Moshe Cohen and Walter Vanderheiden from Sodius-Willert. Moshe Cohen is a senior product manager for IBM's model-based systems software engineering solution. His professional career has all been in automotive, medical, and A&D applications. Moshe was part of the team that brought Rhapsody to market and later extended it with specialized add-on solutions. He had several roles of managing development, technical sales, and more recently in product and portfolio management. Moshe has a bachelor's degree in electrical engineering and master's degree in math and computer sciences from Ben Gurion University in Israel. Walter Vanderheiden is a chief technical fellow at Sodius-Willert and a renowned expert in UML, SystemL, and related standards. For decades, Walter has been focusing on advancing development of embedded systems and software through modeling techniques and lifecycle integration. He's been driving numerous successful client projects in automotive, A&D, and other regulated industries. In addition to working with clients, Walter shares his expertise as an author, coach, consultant, and a trainer. Walter holds a degree in informatics, computer science from HTS and Enschede. Well, Walter and Moshe, that concludes the intro, and the floor is yours.
Thank you, Kara. It was a wonderful introduction. Yes, this is Walter van der Heijden speaking. I'm doing this presentation. We would do a presentation, but unfortunately, it was technically a bit difficult to get the slides to Moshe's side. But he is here, and maybe you can give a short sign, Moshe.
Yep, I'm here, and the intros that you read, Kara, sounds pretty impressive. Thank you.
Yeah, I would hire that. I would hire these guys. Okay.
Nice work, guys.
Good. Yeah. This is first I give you a small presentation about the IBM Rhapsody AutoSAR extension, and then in the middle of this presentation, I will make a small cut, and then I will give you a small demo of the possibilities with this AutoSAR extension, and after that we just do a wrap up in the presentation, and I hope there will be I hope there will be time enough for you to ask questions, and then we will answer some questions there. Good. We have been introduced, so we can go on to the next slide. So the Rhapsody AutoSAR extension in a nutshell. The most important thing is actually quite small and standing there on top. That is the OMG Systems Modeling Language, or SystemL for short. And that is the basis of this AutoSAR extension. It allows people to use standard SystemL system modeling language to design features in cars. So name a feature and you can make your system modeling model without really caring about what you are doing later on in AutoSAR. AutoSAR is I'll speak later about it, but that's the platform where car software is designed with, and this is divided in two platforms. There's a classic platform, adaptive platform. We'll speak later on, and you can see by the arrows that from this SystemL we can go to both these platforms. The older classic platform, which was designed for smaller CPUs, which is a decentralized architecture, many buses in a car, and many connections in between that. A C-type operating system and all more programmed in C, and dedicated buses like a CAN and LIN to connect between these ECUs in the cars. And you know, cars from a couple of years ago, they had hundreds of controllers, maybe 150 controllers, and they were all cooperating to make your car drive, to do all the functionality in the car. Could also be connected to the adaptive platform, which is made for autonomous vehicles, ADAS, advanced driver assistance systems. Also, the multimedia systems that much larger CPUs, 32, 64 bits, based on Linux or even on containers or on virtual environments. It's a more centralized architecture, and as you see in both of them, once you are on this platform, you can also use the UML, the Unified Modeling Language, to create software models and to generate code, production code from these software models, and then incorporate this code into your AutoSAR environment. Good. Yeah, I want to first like to speak about some of the trends in AutoSAR. You probably know a couple of them. Maybe you do. You do know another one, some other ones that I can speak about. You don't know it or you don't realize it, and you might even not be acknowledging them. But I would like to speak about a few of these trends without beating them completely to death, of course. So, technical trends. I spoke to you about classic AutoSAR and adaptive AutoSAR, and it sounds always a little bit like the classic AutoSAR is the old platform and that's going away, and we have a new platform and that's the adaptive platform, and that is not entirely true. Of course, some of the classic will be replaced by an adaptive, but a lot of these classics will still stay there because you will always need sensors, actuators, and other smaller controllers. It's just that there are way less of them and they have a different task inside the car. So the adaptive platform is not the replacement of the classic platform, but the improvement of the classic platform. And as we see in the lower part of this slide, the 100 150 ECUs, all classic, like I have in my car. My car is relatively new. I have a German car with one of those stars on the hood, so that's easy because in my country there are a lot of bikers, and then you can aim for bikers if they don't drive if they don't drive right. But these cars, it was designed about 10 years ago, so this still has the 150 ECUs inside there. And to the newer cars that you see coming out now, electric vehicles, that have far less of these ECUs, and they have very big supercores inside there, where adaptive platform is introduced, and that does a lot of things. All these functionalities can be integrated or centralized because most of these functionalities cooperate very hard together. Older cars, very old cars, had a brake pedal, had a gas pedal, and had a steering wheel, and these three functions had nothing to do with each other. But in modern cars, so steering can be done with the steering wheel, which has no direct link with your wheels anymore, although people think about it, but that's not true anymore. And you can also steer by braking on one side of the car. And you can also steer by putting torque on the other wheels of the car, the outer wheels. So this is all possible. And the cooperation of that makes it easier if you have this all-in-one controller. So other trends, the AutoSAR, introduction of AutoSAR, and also AutoSAR adaptive, and the newer way of creating ECUs for cars also blurs the boundaries between the OEMs, the real car manufacturers, and the suppliers. In early days, manufacturer would focus on designing the functionalities of a car and then giving everything out to tier ones, and they give out to lower tiers to develop ECUs, and then get the ECUs back and then try and test it and incorporate it in a car in a test environment. But with everything on one controller and making the own controller, the OEMs are their own tier ones, and they have a lot of functionality in there that is for them too strategic to just outsource. And it's knowledge that distinguish them. How you distinguish one car from another car brand is nowadays in software. There's no, okay, there are some logos on there, and yeah, BMW has a different feeling than a Mercedes. Sorry, I don't know the German car types, but that's most of that functionality is in software nowadays. And the secrets of that software are things that OEM would like to have for themselves. So the tier ones were originally focused on implementing, but you see them more and more, and the other way around, implementing completed parts of a car so that they can deliver a complete subsystem of a car. Sorry. AutoSAR, other trend that is going on, is affecting the value chain dynamics. Earlier days, waterfall, OEM designed something and then threw it over the wall, and the ECU supplier would develop it and then threw the ECU back, not literally, but as a matter of speak. That already changed into a much more agile and iterative process where stuff goes back and forth and back and forth. In the AutoSAR times where not only requirements were just thrown over the wall, but also something called an ARXML file with a definition in there in how this controller should be working. And that was already a process which would go back and forward a couple of times before the really decisions were made. And this is now changing slowly into an agile and interactive across a much larger value chain, because all this software, of course, running on one controller has stuff to do with each other. You need to think about how this has to work together and cooperate with each other. Good. V, it's still the V, but the V is not the V as in we start on the left top and we end on the right top. And in the meantime, we just go as deep as we can into the bottom of the V. It's not a time-based V anymore. It's an agile V, and it's a place where all the certain artifacts that you have during development are placed. Digital thread, of course, it's still that. This is not still. It is very important to have a digital thread, to have all your traceability information, and you know exactly on what part, why is something there, who did it there, and so on, and why is it connected there, and all these questions. It's driven top down, bottom up over combined workflows. Technical negotiations with by having this exchange format between OEMs and developers and tier ones means that this is a point of negotiation. What is in that file and what is not in the file, and what should be in there, and so on. And process is becoming even more and more important. The more people are involved, and certainly more people from different companies with different interests in the development process. And the more important it is to have your process really nailed down and do it in the exact way as it should be. Good. Now, AutoSAR main workflows. We do the high level first, and after that, I will do a small demo in how we see this AutoSAR workflow. So, basic workflow. You put this slide before I saw that, but I didn't realize it then. So this is the basic workflow of AutoSAR, and as you see, we start on the left top and we end on the right bottom. And you start with requirements. Doors next. You could do other things, but well, why not doors next? Works perfect. And or with or with existing Rhapsody models that you already have. And this all lands into a SystemL functional design. So you have a certain functionality that you want to create, and this functionality is being implemented into SystemL without or with almost no consideration of what you are really want to do with AutoSAR inside there. That is the goal of it. I mean, can't be avoided totally, but it can be avoided largely. That means that you can have system engineers that think like system engineers and make functionalities for a car as a system engineer thinks. This allows you from SystemL to do early validations against the requirements. So you have a couple of requirements, you implement one by one, you implement all these requirements, and with model in the loop, you can see what these requirements, how these requirements need to be implemented and test them. I will show you that later on. Then, from this functional design, you can, with the AutoSAR extension, with the tools inside the AutoSAR extension, create. Get a reminder that I have a GoToWebinar. Yeah, really? So you can create an AutoSAR architecture design. So you have your SystemL, and then with help of an AutoSAR architect, you can create a design that you need to make to implement this in AutoSAR environment. So this is the AutoSAR extension that takes care of that. You can also, of course, import other stuff that you have from the various suppliers that you have in AutoSAR tools, Vector, Electrobit, Siemens, but also the MathWorks, Simulink, or even Rhapsody, as long as it is in the ARXML format. And you can also export it from there. You can say, okay, I have my architecture design made, it is ready for AutoSAR. You export it and give it to somebody else who can then use this into an ARXML or in an AutoSAR authoring tool and generate the RTE functionality there. And what you can do with this with this AutoSAR model, with the same tooling that you have in the AutoSAR extension, is you can create a UML, or as we internally like to call it, ARUML, AutoSAR UML software design. So you can, when you have in your architecture, you design software components, and you design what you want to have implemented, the behavior of these software components. You say what they need to do with requirements, and in your SystemL, you already made the functionality. You show what they need to do, and in this UML, you can make the implementation in normal Rhapsody, as people are used to work in Rhapsody, state machines, activity diagrams, and so on. You can then generate code. You can also import, reverse engineer. You can import the RTE code so that you can use the RTE functions inside Rhapsody by using the control space functionality. And you can co-design this also with other software components that you make with, for instance, MATLAB Simulink. So you can use the verification and validation using test conductor, and you have production code generation. This process, I clicked somewhere else, yeah. This process is actually being divided into two parts. So this is the working flow part, what an OEM should implement. Not should. That's perhaps a bit too demanding, but this is an example of an OEM workflow. So the top part of this, starting with requirements, having older models in Rhapsody, make a SystemL model of your functionality, validate it against the requirements with model in the loop, and then when you're ready, export it using the AutoSAR extension into an AutoSAR model, a Rhapsody AutoSAR model, so that Rhapsody can model as AutoSAR. So you have an AutoSAR model where you can visually see all your AutoSAR artifacts, and then export this, and then deliver this. If you have a second chain, a supplier that is not using Rhapsody, or is not using IBM tools, or is using very old-fashioned tools, you can just say, okay, this is an ARXML file, and here are requirements. Be happy with it and deliver it back. But that's not the modern workflow. The modern workflow for a supplier, of course, is that they just get the AutoSAR file, have it in Rhapsody, and then use the AutoSAR extension tools to create UML design for the parts that they want to implement in Rhapsody, or create other ARXML files for different tools that they want to do, hand coding or Simulink, or even other examples. And then in the end, they can just verify and validate it, and then deliver the code to some integrator, or maybe they are the integrator. That depends on what they are. Good. So, and this is of course the complete workflow when an OEM is its own supplier, where you see that the export is not necessary; it stays inside their own system, in our own system. So, a bit deeper in the key aspects, but I will leave that for later. I will now switch over to Rhapsody and to my own workflow. I should still have the other big pictures in there. Moshe has exchanged these, and they're now black, and they put the IBM blue in there, but I think you can still see what it was. So what I did, I have these three different models. I have them all three, of course, and to show you exactly where I am, because it can be confusing at first if you have never seen it before. So that's why I made this. So I made a circle or an ellipse around this. You see, this is the system engineering model. This is where I start. I have gotten requirements, or we make requirements, and these requirements in this case are all indoors. I can show them to you. Oh, okay. Well, they are in here, but for some reason, I think that the connection is a bit it's not too well. I'm in a hotel room with a cell phone connection, so you have to believe me on word that we have requirements in here, and then from these requirements we just take one by one the requirements and start implementing them. Not implementing, but start designing them in system engineering. And how do we do this in system engineering? Well, okay, first I have to tell you, of course, what we are making. This is a very simple application. This application is an interior light of the car. The very simple version in all the cars was, of course, switching the door. You open the door and the light would be switched on, and when you close the door, light will be switched off again. And this is the electronic implementation of that. And of course, this is the first standard implementation. It will be extended with things like, okay, you close the door, but the light stays on for a while, and the light doesn't go out, but it will be dimmed a little bit, so that you can find the keyhole where you have to put your key in, or the key where the button where you have to start the car with. Good. So I go to the overview of this package. Let me show you the sequence diagrams first, because how you implement this with using Rhapsody with SystemL, you have a process normally. I've implemented our own process, just make sequence diagrams one by one of all the scenarios that you can find within the requirements, and the requirement opening a door and see if the light goes on, closing the door, and then the light goes out, opening another door, open 2 doors, and then close 1 door, and that all has different outcomes that are all different scenarios. You implement all these scenarios, you make tests for all these scenarios, and this is basically how you work. You can also use processes like Harmony from IBM, where people do stuff with, but it's also supported by Rhapsody with a lot of helper tools where you can just right click and then let Rhapsody and let the helper tools do a lot of things for you, like allocating to different blocks and so on. Good. So I have one sequence diagram. This is opening the door. Just ignore the run, because these are the things that are normal in the car. You have to put the car controller all in a certain mode, and we made the starter in there. But if you see here from the door, this is the left door, and the left door is opened. And when the left door is opened, it lands in something called Light Manager, and the Light Manager says, "Okay, there's a door open," and that means that I have to change the status of the light to on. And when the door closes, and it was the last door, then I have to set the off to the light. And so you can make a couple of these sequence diagrams, implement them, and make tests for them, and then you can start them. So what you can do in system engineering is you can add behavior, simple behavior with events that are being sent back and forward. And if you do this behavior there, you can also test this. So when I run these executable, you can see stuff is already happening. It writes some stuff, and you see that I made a small panel there to run a simulation there. So we implemented this. I start this, and all I have to do is press the init panel and press the run button to make sure that we're in the run state. And when I now open a door, which I have simulated by doing by making a switch, then you see the light has been going on. I can open another door, changes nothing. Can close the first door, changes nothing. Close this door, and you will see that the light will go out again. And this is the back door, and it's also opening there. So this works. And I also created a test package here. This is Test Conductor, a Rhapsody add-on tool that can help you to create test cases for all these sequence diagrams that you have. But you can also make auto tests in there. When I switch over, I don't even have to switch over. I think I can just go into my test package, and then I take one test package, and in the test, you see that I have a test context, and here I have a couple of test cases. And let me just create one test case or execute one test case. And you can see how this works. This is just a test case, which is also a sequence diagram where I have a scenario, and I just can automatically let Test Conductor run this scenario. This is only one, but I can have hundreds of tests, and Test Conductor can, every time I just check something out or do something, I can let Test Conductor test this. It can even be done in a Jenkins or a continuous development or continuous integration environment. And so okay, you can check that if you added something, that everything that you did before is still working. So, and when you're done with this, you have a system engineering model then that works fully to your satisfaction and say, okay, this is exactly what I need. Then you can go to the AutoSAR extension. Part of this AutoSAR extension is called M2M. M2M is the model-to-model transformer that can take a model in a certain domain and then convert this into another domain by using rules. And we have a couple of rule sets, standard rule sets that are changeable, of course, by the user. So if you have your own process and you have a couple of things that are not standard as people do in a SystemL, then you can change the rules easily and then take care that your SystemL variant and your SystemL process is also being mapped on AutoSAR. You see here we have a SystemL to AutoSAR. This is for the demo, so that we know which one it is. And I can right-click on this. I can show you a couple of rules. I have a table here. Let me close this. So you see here we have rules where we see what source meta class stereotypes have to be certain target meta classes, target stereotypes. There are also M2M is a bit smarter. You can have condition functions to check if it's really the right element that you have, and you can have post-processing functions or new context functions, or you can also create other elements that are not in the original in the original domain now. So, and you click right on this, and then I can say M2M launcher, and I launch the M2M. Say I want to have another model. Click on transform project. So transformation was completed successfully. Should have a, yes, exactly. It always disappears. So I can have a log file, and in the log file, it tells me exactly what it all read and what it all converted, and for all what it didn't convert. And that's, of course, very important if you have a situation where you do certifications afterwards, that you know exactly, okay, these are the elements that are not converted. Why are they not converted? That you still have your chain of traceability. So when I click on quit, then my target model is opened. The other model is still there, of course, and my target model is an AutoSAR model. And you can see this by because we have now AR packages and so on. So, and I can go to a software component diagram, to the overview. It must be in the other package. Okay, this is it. Sorry, I have the wrong diagram. This is the wrong. This is the correct diagram. This is the same diagram as we saw before as a SystemL with blocks, and now you don't have blocks. You have application software component types, and there is a root software component type. It's not on this one. So, and I can check this and look into this, see the light manager, see that I have all the elements that I need in here, that I have ports, and that I have connections with other stuff, and that I have variables and runnables and interrunnable variables and so on. Now, this I can, with the AutoSAR toolkit, with the AutoSAR extension, I can say, okay, please take this, what we made here, this architecture, and please export this for me into an XML file. Okay. Takes a while, unfortunately. If you wait for it, it's always longer. So, but it's ready, and let me switch to my beloved Total Commander. I'm an old guy, so I grew up with Norton Commander. I cannot live without this. So, and here you see, I will show you into the file, and this is this is a normal ARXML file with the it's XML, so you can read it. I read. Okay, it's readable text. And this one can be exported and or just copied and given to somebody else who can implement this. So, but suppose we do not only want to do this, but we want to have a where's my other Rhapsody? I got two Rhapsodies open. This is the wrong Rhapsody. This is okay. I need to quit. So this is the right Rhapsody. Sorry. This was my AutoSAR model, and from my AutoSAR model, I can also do the same trick now as we already saw in the demonstration. So I take AutoSAR to AI UML, right click, to the M2M launcher, and have to browse for the correct document. and transform this project. To speed up things, I've already loaded this project, the result of this. And this is the AR UML. So this is where I start to implement certain software components, as you have here. And these software components, you can see them inside here. They are in my AR packages, in my application package. You see here, software components, door, front light actuator, light manager, and so on. And I can take all these software components and implement them and make a small implementation. And you have here the normal things that you know, attributes, but also a couple of things that are necessary for AutoSAR, for an AutoSAR environment. They're automatically added to one if you want to do something inside Rhapsody. And I have here normal classes for normal implementations. But I can also have things like state machines. So this is a normal Rhapsody state machine where I have the where I implemented the algorithm to start the light when doors are opened. So I have all doors closed, and every time a door is opened, it goes to a different state until it's back here. And you see here also inside the state machine where you can call functions inside Rhapsody. You see RTE right status, right front light status SP. These are the RTE functions that we have reverse engineered, which were generated by our RTE generator, which is external. In this case, we use the Siemens Mentor tools, but you can also use Electrobit or Vector or whatever tools you want like. Good. So when we have this, of course, you also want to see, okay, is this working? Of course, this is working. I can show to you that it's working. And oh, I clicked too fast. Come on. Okay, so no, should be in the middle. So you see, I already had the Visual Studio open, and what I do now with Rhapsody is I generate code, and it's not generated now into an AutoSAR environment. It's generated in Visual Studio because we have a test environment with a mini RTE that we made for Visual Studio, so we can test this software on a PC for the first time now. And I already opened this, and you see that generated code needs to be reloaded because I generated all new. And I can start this environment here. Okay. And you see it is running, but unfortunately, I don't see much. That's not too nice. Oh, let me stop this. And you see it's stopped and here, but we have something which we call the embedded UML target debugger. It's a tool, also part of the AutoSAR extension. And in the AutoSAR, this is built in, and this can connect to a running target, to what is running in an AutoSAR environment, or in this case, was running in Visual Studio, and has the ability to show you the diagrams that you have, the sequence diagrams that are running inside your environment here. And you see when I started here, you see the environment is running. Let me switch off the auto refresh, then it's a bit better visible. Unfortunately, this is an AutoSAR tool, so it is just polling, and you see a lot of polls, but we can do something about this. We can create a new view. Sorry. So I can add a filter, and in this filter, I can say, let me make a new one. So, and I want to see events here, and I can see, okay, I want to filter out my timeout events. Oh. This is not what I want. Okay. I'm a bit too quick for what I have. And I can say apply filter. And this is a filter in my environment now. And when I click here, you'll see nothing to see because it filters out all the timer events and you don't see anything. But what I can do now is I can say, okay, I just go to my event injector, which is part of this tool. And in this event injector, I can just select an event. I already made an event. This is debug open door, and it does a couple of things because you can save sequences of events with this. So you can make small test situations here. So that stuff is running a bit faster. So I will send this to my door 1, and I will do inject event. And then you see that from my environment, the door gets the door open, and it sends the door open. And here you see that one door is open and my light is on. I can send the same thing to my door 2, inject event. And you see second door is open. And let me just take door 1, and I can do debug close door. inject event, door is closed, and I send it to the other door as well. And you see that here the light is being switched off again. So this works. As I said, I can save this and then do all kinds of nice things with it. And good. So I will stop this. The other thing I can do, and that's I need to load another model for this, and that is this. Let me test project. Yeah, I implemented this in another model. I have to merge these models, so you have to forgive that, so not me, because we can do the same thing, but then with test conductor. And okay, I forgot, of course, to close this one. Target debugger is closed. So, and I can just, with this also the same way, I can just look into my tests and take one of the test environments, right click on it. Oh, sorry, I have to open the test, the target debugger first, because this environment is relying on having the target debugger available. And okay. Then I can right click and start the test here, execute test package, and do the same thing. And this also works, of course, in an environment that is oh, good. Demo effect. So normally it will take the target debugger and will execute my my environment and connect to the target debugger, and the target debugger will connect to the test conductor and say, test conductor, exactly what has happened, and gives it back the sequence diagrams that it took from the target environment. And the test conductor compares it and say, okay, it's good or it's not good. Cool. So back to the presentation. I want to go a little bit deeper into the key aspects of Rhapsody AutoSAR extensions. SystemL UML, front end for AutoSAR. Is this a front end for AutoSAR? SystemL is already widely used in automotive for modeling requirements and for modeling logical design. And the new SystemL, there will be a new SystemL. It's already defined, and they're still working on it, but most of the things are released in the meantime. It will have a more stronger focus on system engineering, and will also have a better transition to software, but also mechanical and electrical engineering. And this is, of course, still under investigation. People are working with it, but they try to get a and what SystemL 2.0 is that it's its own meta model. The previous meta model was based on UML. There will be a coexistence between SystemL v1 and v2 for quite a while. That's our expectation. Most tool makers are not creating completely new tools, because that was how SystemL started a long time ago, to make it as close as possible to UML, so that tool makers could use the same tools to do SystemL as they do UML, as Rhapsody does. Good. UML, executable. SystemL, sorry, is executable in certainly in Rhapsody, or you can do a simulation, but the simulation is done by executing models. UML, same thing. You can generate code, you can execute it. It's also really widely used in automotive for software design and sometimes code generation. There is a smooth handover from SystemL to UML by using Rhapsody, of course. Automated production code generation. What comes out of Rhapsody is production code, and is being proven in a lot of. I have a slide later on where you see a couple of instances of that. And automated support for model-based testing and early verification and validation with Rhapsody, of course. Nice thing about UML and SystemL, of course, is these are open standards. You can it follows a complete standard. Yes, people have comments about it, but the standards are always as good as the standards are defined. They're defined in English, so there are always points where you say, but they stay as close as possible to the standard, and they are really ready and willing to adapt to standards. We can do co-simulation with Simulink via profile. We can read and write files to DaVinci, for instance, but also other ARXML files. But UML SystemL, by using XMI standards, can be exchanged with other tools as well. The IBM AutoSAR extension is open by design. So import, export standard ARXML files we leverage OSLC, of course. As you saw, I have doors requirements inside there, doors next requirements, but you can also use all other OSLC tools. We do code simulation of Simulink, as said, doors requirement connections, integration with all the digital thread global configurations tools that IBM offers. Rhapsody has a COM or a Java API, so you have complete control over your models via this API. That's exactly how all these tools are made. And we can reverse engineer legacy code in that. So automatic production of code generation. So if you only do model-based design or analysis versus you doing code generation, you're saving massive amounts of time. If your model is automatically also your code because you generate your code from your model, that is saving time. It also delivers you direct traceability support to inside your code. If you generate code from Rhapsody, you will see your requirement text inside your code because there is a link there, there's a traceability link. And so even when you look only in your code, you can see, it's this requirement. And it's automated. It's not that somebody typed it in by hand, as people always did this. You preserve the full behavior, everything, dynamic instantiations, interrupt service routines, everything. Okay, it's not as necessary, of course, in AutoSAR environment, but Rhapsody is not just limited to AutoSAR. You can do a lot of things with the Rhapsody, and that is sometimes needed. I know from my own car, I have keyless entry, keyless go, and I know that the key is not an AutoSAR. It doesn't have a CAN bus. As my wife always says, it would be nice if we had a cable, because I then could see how far you are from home, but it doesn't have that. Good. Quick response to changes. If you change something in the model, there's a new requirement coming in, the code can be generated from that model. So it is way quicker than, okay, I made a new design, throw the design over the wall and somebody else is programming that. And before they understand everything, and I did this in practice. If you have time later on, I can give you a very nice example of how this really worked with modeling and with code generation. Fully testable. Test conductor can do way more than just having a sequence diagram for a test. It can do MCDC reporting. It can do coverage, total coverage from everything you do, model coverage, requirement coverage, code coverage. It leverages model-based testing for early verification, validation, and complete testing. It is always certifiable. Certifications, all the certifications, 26262, but what is the ref from 61508, all these, they all demand a method for having your designs. So if you do this modeling and you generate the code, and nowadays this is recommended, if not mandatory. And the code that comes out of Rhapsody or code generation is of much higher quality than handwritten code, because the code is always written in the same way. There are code frames, of course, that someone types in, but you have no chance to just do something in a fundamentally different way. The code generation takes care of that. Believe me, I have 20 years experience in that. That's one of the biggest advantages. These are a couple of examples where we already had code. It's not all automotive. We helped Sennheiser to make their conference systems, and don't understand this wrong. This is high real time. If there's 1 millisecond, not 1 microsecond there that you are wrong inside your timing, that you hear that in the sound. People are very sensitive to that. So you need to have this real time fully as good as possible. So Sennheiser did this with code generation, full production code generation. We made a code generator for a car manufacturer, GM, where they generate all the code for their body controls and their AutoSAR systems. This UML code generation, Daimler Marquardt. Daimler had defined keyless entry, and they let Marquardt make it, and we helped them doing this with Rhapsody code generation. Passive start entry system at Continental Automotive, code generation. The satellite navigation for the Galileo satellites, the European GPS satellites, they are made with Rhapsody. A400M flight controller, we made the ADA code generator for that. The Mika missiles and other mission control system software is all made with Rhapsody. Good. AutoSAR applications are getting more and more complex. I'm sorry. Do we shift left verification and validation now? So leverage for modeling and virtualization and simulation for early testing. So the earlier you test, I don't have to tell you all if you are in this presentation, you all know it. the errors that the customer finds are the most expensive errors that there are. So the earlier you can start testing, and the earlier you can figure out, is this working? It's also for if you have a new kind of system, you thought of something completely new. You want to test this, and you want to verify: is this feasible? Is this really working? Are there any other errors in there? So you can identify fixed errors, and to achieve product quality out of the box, you can push the button, generate code from that, and you can be sure that this is the best code that we can produce for this. So you can do this for AutoSAR function design models and for AutoSAR software design models. So the early verification and validation is an integral part of the ELM automotive compliance solution that we deliver here. Good. So compliance with industry standards, we are aligned with all the IBM LM tools. Also the full ELM tools can, of course, in Rhapsody, can connect with Rhapsody and have also C connections with Rhapsody, with EWM. I always get mixed up with the abbreviations, and IBM changes them every 2 years, so then I forget one or two of them. But I have Moshe, so Moshe can help you there if there are questions. And we provide an agile process for automotive, so you can do this as agile as you want. And this will kickstart your model-based system engineering journey. Good. Out-of-the-box reporting, offered, of course, by all the tools that are there, and compliance expert content. So people who know their way around compliance, they're experts, and the content is coming from there. So, small summary. The main capabilities is that we integrate system design and software design into Rhapsody. It was always integrated, but we made the AutoSAR extension to make sure that this is also working for your AutoSAR environments. Integrating classic and adaptive workflows. We have focused on classic first, of course, because that's still the market where this also helps most. But we are working very hard on our adaptive workflows as well. Standard graphical modeling to design very complex architectures. I don't have to tell anybody that the things that we build in cars now, and I don't even speak about autonomous car, but also simple functionalities. If we only look at this interior light, because I thought, okay, this interior light, how hard can it be? And then people started asking me, okay, why haven't you implemented this? Why isn't there? There's also an airbag signal. If the airbag comes out, the interior light goes off. What? Okay, it is complex, and to design this with just a model and then afterwards making source code is just too hard. Automated production code generation, that's what we also integrate. Focus here is on automation and productivity, so that most of the steps that you do, you solve the M2M steps, the model to model, the transformation, you make a transformation once, and then you can push button, or you can even put it in your CI/CD environment and do it automatically. Should be automatically. Everything that is not done automatically is error prone and can be the cause of error. So you want it automatically, and it can be done automatically, and we focused on that one. So we hide the complexities of AutoSAR for the people that do not need to know them. So if you do system engineering, our focus was on getting all the AutoSAR out of it, so that you do not need to know it. And in a later phase, when somebody really knows his way around, can say, okay, these are the parts that we take out, and these are the rules that we need exactly to create our really correct AutoSAR files, so that engineers can focus on the right questions, not on the this client server port, was it implicit or explicit? You don't want to know. You want to know, okay, this ADA system, okay, X happens. Now Y needs to happen. Yeah, that's why you want to focus on. So you can integrate this AutoSAR in a large development process and in a digital thread by this AutoSAR extension. Good. What are we doing next? Sitting still and drinking beer? No, we are continue to work on other stuff, like support more advanced workflow, classic to adaptive, systems architecture. I always forget what the abbreviation. I don't explain it. Yeah, service-oriented architecture. Yeah, you know why I have difficulty with that much. I will not explain it. Combine classic, adaptive, and service-oriented architecture workflow, and mix AutoSAR with non-AutoSAR designs. Yeah, so as I said with the key, but there are multiple examples of that. And Rhapsody is capable of that. You don't need AutoSAR. You can just push the button and make a complete application. V&V capabilities. We want to do software in the loop testing. want to make connections between the system engineering and the software, and then use the tests that you already have used and to create tests that you can do with parts of the software, with your software components. We want to have a deeper integration with the Siemens AutoSAR offering, the virtual ECU, the capital ECU virtualizer. We're already working on that. And of course, use the RTOS and middleware from the Siemens adaptive AutoSAR solution. And a deeper integration with electrical, mechanical, and network flows. So together with Capital, with Siemens, we will integrate a lot more of this. And also using Red Hat Linux as a CI/CD platform for the continuous development, test, and deployment. Good. Oh, click. No? Yeah, that was it. Oh, Moshe, you forgot my number. Man. Okay, then bottom Moshe. Good. Oh, that is nice in time, I guess.
Yeah, we're doing great.
Yeah, I always like to be ready in time, not later.
Well, we have a number of questions, Walter. If you have a few minutes, we can
cool.
get those addressed. Okay.
Yep.
So the first question,
cool.
So it's, did I misunderstand, or does the red light next to test cases imply that the test case failed? And this goes back to kind of your slide with the automobile.
Oh, the second one. No, you understand correct. No, not the test case failed. For some reason, I couldn't start the test case, so something failed. Most of the time, I test this. I did all test this, but it can happen that doing it the second time says, something is already done. I don't do it. So yeah, it was a demonstration effect.
Okay.
But pay good attention.
All right. How does SysML validation work? It assumes some type of action specification language, correct? How does that relate to actual software model to stay consistent in actual ECU?
Okay. ECU and SysML, we try to keep this as far as possible out of each other. So this is a functionality that you create with SysML. The whole point is that you use normal system engineering and SysML. And in Rhapsody, SysML and the simulation of your system engineering model happens by using, and I can even show you, this is my system engineering, that was my test project. I got too many of these projects to open now. Let me close them and then open the correct one. And so how you do this? You do this by using normal C or C++, in this case C++, inside this, and state machines. So when I open this and I open my system engineering model, that's this one. Yes, make it full screen. This is a virtual image that I access via my cell phone. So it is quite fast, but in this case it's a bit slower than normally. Yeah. So this was the simulation that you saw. And I can also show you in the packages here in my interior light package that I have a couple of blocks, and that these blocks have state machines. For instance, the light manager has a state machine. So I can implement the state machine. These are the run states, and here it's just a state machine where I just respond to events. This is how you normally in Harmony do stuff. You send events back and forward to respond to stuff. And in the state machines, you respond to it. And you can, if you want to print something, and that's all, these are just C++ statements that you put in there. So Rhapsody simulation is actually execution. The nice thing about this is that stuff is already executing, in this case on a normal PC, so you know that it is running. And then you can also make the connection with things like test panels like this. These are, you can make them dynamically, and you can connect them to elements that you have inside Rhapsody and say, okay, this is a button, so you connect this to this button, and you can change an attribute, and this will automatically be taken over. So it's a bit of programming, but programming on a system engineer level, so nothing difficult. I hope this answers the question.
Walter, you can also add that when you use SystemL, you really focus on the logical model, the behaviors, what should happen when something happens, and so on. And you don't make concrete design decisions on how this will be implemented. In fact, the same system model can later be implemented maybe in all software or in a bit of hardware, but then other other parts in software, or some will be classical, but the same behavior, the same logical model can later be implemented as adaptive AutoSAR. So the idea is that you don't make early design decisions when you use SystemL to develop the logical model. These design decisions will come later on.
Yep. This is purely, I have a functionality and I want to implement this functionality and see if what is all related to this, does it all work? In this case, the doors, as I said, as a small example, somebody comes in and says, hey, I want to have the interior light on when the airbag goes out. So in case it is still working, that the people who do the rescue, that they might have a bit more light than without this. So this is an actual requirement. I know that by accidentally. So, and all these requirements need to be implemented. You get all these requirements, you implement them, but you do not want to think in this moment, I need to have a hardware, this is a sender receiver port, I guess. You don't want to know this, and you do not want your system engineer to think about this. So it's really focusing on the logic here. And in the second step that I show you later on, then you say, okay, now I want architecture, and then you do behavior.
Well, it is more than this, because in many OEMs, they create libraries of these logical models. And then later they say, okay, for this car model, year XYZ, we are going to allocate these features. And then later, when they see the collection of features, then they decide how to implement all these features and so on. So there is a very important role for these logical models that are design independent, and only as they're being allocated to certain car models, only then you do the concrete design work.
Okay. Next question.
Any more questions?
Yes, we have several. So we can decide if we want to go over by a couple of minutes or how we want to handle it. So if SWC are implemented outside of Rhapsody, say in Simulink, how does validation in Rhapsody stay consistent?
Nice question. For instance, Simulink, so the implementation of the software components, there is a step before this, and that's why you do the validation in Rhapsody, and you can validate your components that you are going to make in Simulink, or models in Simulink. You can co-simulate them. Unfortunately, I don't have that by hand. It would take too long. It would take half an hour to show that, but it is possible to, in Rhapsody, have a block that you call Simulink, and then connect this Simulink block to a real actual Simulink model, and then also control Simulink, or the other way around, have Simulink control Rhapsody. So you can do both of them. So in this case, for instance, if you say, if I close the door, then for 1 minute, the light stays on, and then the light needs to be dimmed down, not just switched off, but really dimmed down. And the dimming down is something that's a PI loop, or I'm not sure if it's the correct expression, but something like that. This is something that Simulink is really good at. And Rhapsody can do it, but the model will not give you any help in there. So Simulink can do this. So you make a Simulink block and you say exactly what to do there, and you make these blocks together and you let them work together in SystemL. And then when you generate the code, you can incorporate that code inside your Rhapsody model as well, very easily. And because you are then on an AutoSAR level, AutoSAR has these ARXML files that we write. So we know everything about this block, and all the AutoSAR environments know about this block. So if you have your simulation environment or your run environment, this run environment is used to doing this and simulate this if one part is not there or the other part is not there, or even taking both parts of that. So that's what AutoSAR is all about, that you know everything about another software component without actually knowing how this software component works. That's the whole point.
Great.
So I have a lot of noise here outside. I hope my microphone's not picked it up.
No, we don't hear it.
No.
Yeah. Next question.
Okay. Systems design is usually done by system engineers, and their SystemL doesn't directly map to software architecture. How does this workflow look in Rhapsody?
Yes, and I don't have the complete example here, and I worked on it this week, but we didn't make the demo ready, unfortunately. It works by more or less by using as you use the harmony process. You here select the blocks that you want to use inside your AutoSAR environment, and define the blocks or define multiple blocks out of one block and make them software components. And you do this with partly with harmony related tools and partly with the M2M rule sets that you have here, so that you can take them and say, okay, I have these blocks here, and this block here, for instance, needs to be a software component inside my other block. And I have here ports, and these are normal proxy ports which send events, but M2M, the AutoSAR extension, has rules where you can tell exactly, okay, I just sending events now. That's not exactly what I want, because that's something that AutoSAR does not support or does not really know, but we have something else here. And these rules are converting them, and then you create your AutoSAR model. And in this AutoSAR model, you automatically have your software components, which is your first draft of your architecture. Then AutoSAR architects look over it and can make changes to this, and even using M2M.
Let me jump in here.
Give the changes. Yeah.
Let me jump in here.
Sorry.
It is much easier to show than talk about it. So whoever asks a question, if you want to know more, please contact us, and we'll be happy to just to show you this in action. It is just hard to follow the steps, but once you see it, you say, oh, okay, makes sense. So if you want to know more, contact us, and then we'll show you.
So we can address additional questions anytime after the presentation.
Of course,
yeah. So let's just read a couple more, and then we'll wrap things up. That's okay. So how would one model distributed multi-core, multi-threaded environment simulation and validation in Rhapsody? How would one model distributed multi-core? Okay.
In SystemL, you do not, as I say, you cores and all that, it's not really important for you. You make a functionality. It's a system that you make. The moment that you start distributing it, and that's a nice thing, Moshe already mentioned it, from one SystemL model, this is of course a very simple model, there will be one software component or 3 software components, and that's it. But if you have a way more complex model, it's also possible to say, okay, we have 3 or 4 different software components on adaptive software components, which are much larger, that run on an adaptive platform, and we have a couple of sensors that need some parts that need to be programmed in Classic. So this model transformation that we have built in the AutoSAR extension is of course capable of taking something and distribute it into Classic or multiple Classic or multiple adaptive environments. And this is where multi-core comes in my opinion. And then you have multiple software components that can run on multiple cores. And the system model is not aware of it, should not be aware of it, in my opinion.
Okay. Just ask the last question.
This is all very, this is all very hard, very hardware and AutoSAR related already. Yeah. Okay.
Sorry about that. Is Rhapsody roadmap to fully supportive? Okay. Is Rhapsody roadmap to fully support behavior modeling to the level of MATLAB and Simulink? If not, how does the traceability work between both tool sets?
Okay, Rhapsody will always be next to Simulink, because Simulink has some features in there. If you make simulation models for I always call it analog processes, that's something that the UML has not in itself. So that's what Rhapsody does not do. Rhapsody does decision logic. So in this case, if you open a door, the light should switch on. This is not a regulation algorithm. And I know people misusing Simulink for that because they have Simulink and they think, okay, that's cool. And of course, if you look at classic environments where everything is pulled every 10 milliseconds, the power window switch in my car is being pulled. Are you pressed? 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 Every 10 milliseconds, billions of times during the lifetime of my car, and only 1,000 times it will be really pressed, which is a waste of computer cycles, in my opinion, but that's just how it works. And this is how the Simulink environments work. And if you have an analog process that you are simulating, that you are not simulating, that you are implementing on a digital computer, this is a perfect solution. But it's being used for everything. I always say, if you have a hammer in your hand, the whole world looks like a nail. So people have a hammer as a tool and they do everything with the hammer. And that's not correct. You have multiple tools for that. And Rhapsody is a much more suitable tool to do implementation of decision logic, as I say. And there's a lot of decision logic. Apart from that, in the rest of the environment, Rhapsody is a fully open environment, and it is integrated in the complete EWM suite. So you have requirements inside your Rhapsody. You can import them, export them, make connections within, have traceability information in there. You can directly link to test tools, the test information, as you see here in this model, my test information, also the test results, and all the coverage reports are all inside my model. I can write my model, I can document out of my model, and it's not proprietary, it's all open. I can just export it to everything, and I can import a lot of these things. And it can also cooperate with Simulink, and it can cooperate with Simulink in testing and verification. It can validate models for Simulink. It can validate its own models together with Simulink models and do communication between them and validate both. You validate your Simulink part as Simulink, you validate Rhapsody part in Rhapsody, and do it together and have traceability. Because we can, of course, give our traceability and all the requirements that we have in there also inside an AXML file to Simulink. And you might even be able to read it in Simulink. I don't know about this, but if traceability is not possible, it's not a Rhapsody problem.
Okay, we have one last question. Go ahead.
We can also with Rhapsody you describe modal behaviors where you may have many state machines, and each of them is in its own states, its own modes. So for complex model behaviors, this is where you're going to use Rhapsody. And with Simulink, it is more for continuous models. And we each follow the same paradigm that you have. It is a model based, and then for the model you go into the code. But the kind of models are very different. And just as Walter said, the two really complement each other. You can try and stretch one to do the other, but it is really not natural. Okay, I got a question here on Slack. Or do we still have 2 minutes? Okay, it is probably either an IBM or a partner because they have access to my Slack here. Okay, I see in the demo that Walter is running a test and the target debugger on the code. So 2 questions. Was this code generated from Rhapsody? The simple answer is yes. Can you run it with the code running on the target? And the answer there is yes as well. In fact, you can run it on the soft target, like a soft ECU, or on the concrete ECU. So yeah, the same code with test conductor.
Target debugger gave it away a little bit.
Sorry, Walter, say it again.
The name target debugger gave it away a little bit. That is runnable. That can be run on the target.
Exactly right. Yeah. Okay, so back to you, Kara.
Okay, final question. Is it feasible to fully describe software architecture in Rhapsody?
Yes. That's the idea, of course. You're using you're using UML. If you want to use something else, this we cannot answer, but following UML for software design, that is exactly the intent of UML. Great.
Well, that is a wrap, I think. Thank you so much for your presentation, Moshe and Walter. It was really great.
I would just add one more thing as I think about this. Okay, when you capture your software, you can even say what you want to be used as an interrupt service routine, for example, and link this to the right registers. And so with the AutoSAR extension, you can also describe things which are specific for AutoSAR. So although the context is UML, there are some extensions which are specific for AutoSAR or specific for real-time systems, which actually make it even more suitable for adaptive AutoSAR. And we leave it at that. I mean, we can talk a lot more about this, but let's stop here.
Yeah, and I would like to thank you, Kara, for all the time that you put in this in your presentation and you're presenting us.
Oh, it's my pleasure. So if anybody would like any additional information, please reach out to us at info@321gang.com. We did record this session. It will be available for playback on our website, 321gang.com, under the resources tab. Should be up by mid to late next week. All right. Thanks, everybody. Bye-bye.
Everyone. Bye-bye.
Yeah, bye-bye. Thank you.